Hello, this is lecture 2 of Applied Nonlinear Dynamics and Nonlinear Control. So this was a graduate course that I'm working on. So let's continue talking about the basics of dynamic systems. So we covered, lecture 1 we started talking about how we describe dynamic systems. Sorry. So we said that in general, we have discrete dynamic systems and we have continuous dynamic systems. And by discrete, we mean that we use a discrete equation to describe the dynamic systems. And so in other words, we use difference equations. And then we also use differential equations. Differential equations is more familiar for those who are, for example, doing mechanical systems or electrical systems. They frequently derive the differential equation governing the behavior of the system, and that's a continuous equation. And then for those who are, for example, doing economy, or for them, a discrete a difference equation is more familiar. But you've got to pay attention that at some point you've got to discretize your continuous equations too. Meaning that, or it's true that we start with, for example, Newton's second law and derive our differential equation. But then once we have our differential equation, when it comes to solving that differential equation, if it was a simple equation, you may be able to derive or find the closed form solution for that differential equation. But for real systems, for most of the time, you need to find a numerical solution. Then you need to use computers, for example, and then for them, you need to discretize your differential equation, and you should have discrete equation. So, in general, we said that a difference equation is described in this form. X sub k plus 1 is in fact our state vector at time k plus 1, then which depends on a state vector at time k, and plus our external input. And then for differential equation, we have x dot equal to f, depending on, in this case, I have this time explicitly on the right hand side. And then I have an input. This is a non-autonomous system. It is called non-autonomous because time appears explicitly on the right. So we have also cases like this case where x dot is f of x and u. X is current state and u is our input vector. In this case, we don't have explicitly time on the right hand side. For example, if you go back to lecture 1, we had this spring mass system. If our spring mass system is forced using an external force, say cosine omega t, then cosine omega t, which is an explicit function of time, appears in your dynamic system, in your differential equations, and that's called a non-autonomous system. The non-autonomous system requires some external force to operate or to continue working. And in a separate video, I talked about specifically about how we can graphically describe or explain the dynamic system. The thing is, on the left hand side, I have x dot. X dot is my state vector. Is for example, if I had my spring mass system, on the left hand side, my state vector constitutes velocity and acceleration. Velocity is found by differentiating displacement, and acceleration is found by differentiating velocity. So on the left I have x dot, and on the right I have xt, and u. So if you think about it, if you go back to your calculus, x dot is essentially if you differentiate your function with respect to time, you get x dot, right? So f specifies the tangent vector at every point x and t, right? This is just basic calculus because x dot is described using f. We can explain f as the tangent vector at every point x and t. Right? Same thing applies here. We can explain f as being a tangent vector at every point, at every x to this vector field. The other thing is that when we say mathematically, when we say f x dot being a function of x and u, essentially f is a mathematical function which maps an Rn function, assuming our state vector has n dimensions, and cross R1 if it was a non-autonomous system, because time is a scalar quantity R1, multiplying Rm because our input could have m dimension. M is not necessarily equal to the same equal to n, the number of state variables, and this function m maps this vector field to this n-dimensional vector field x dot. Now, as you see, as you would expect, the dimension of x should be the same as dimension of x dot, right? And this is for when we do not have an extra equation for example, explicitly for our output. Then we go back to that kind of equations later. So, all right, so why we are doing this? So we said that we're doing this. We use, for example, Newton's second law, find our equation of motion, then reformat that and describe that or represent that in this form, a standard form. Once we have that, which is the mathematical description of the system, then we can talk about equilibrium point. That's our next step. And once we have the equilibrium point or our desired states, we can talk about control, how we can control the system. But for now, when we are in nonlinear dynamics, we haven't yet moved to nonlinear control. So we're going to discuss equilibrium points. And what are equilibrium points? Equilibrium points are the states. If you think about it, if I say find the points where x dot goes to 0, how would you describe that physically? You would say that, all right, if x dot goes to 0, it means that at that point, my x does not change, right? Once I'm there, I'm gonna stay there because x dot goes to 0, and that's called equilibrium point. So if you start a motion, our system from an equilibrium point, we are going to stay in that equilibrium point. So equilibrium points are defined by the vanishing of the vector field. Again, by the vanishing of vector field, it means that f goes to 0 or f, x, and u goes to 0. So, and as I explained, for example, for our mechanical system, if velocity and acceleration goes to 0, and that's our equilibrium point. And we're going to stay there. Nonlinear system may have more than one stable equilibrium point. I'm going to come back to this. All right, so when we have equilibrium points, those equilibrium points could be stable, could be unstable, depending on the sign of, for example, our eigenvalues. They could be stable, they could be unstable. So I'm going to come back to this. But for now, think about this. What is an equilibrium point? What is a stable equilibrium point? What is an unstable equilibrium point? So if you consider a pendulum, for example, an inverted pendulum, and I say, all right, this is my pendulum, and this is a mass, for example, a small mass attached to this, and then I have this one. This is also a pendulum. So if you think about it, physically, you understand from your basic physics that the only force acting on this pendulum is gravity. And as long as this gravity does not create an external moment, this pendulum is going to stay where it is. But let's see what happens in this case. This is exactly vertical along the line of gravitational force. So gravitational force, which points down, if you write down your equation of motion using Euler's equation of motion and write it about this point O, for example, sigma m, the net moment about this point goes to 0. So sigma m goes to 0, your angular acceleration goes to 0, angular velocity goes to 0, and as long as all the initial conditions are equal to 0, this pendulum is going to stay on this position, at this position, right? But you know that from basic physics that this equilibrium point is very unstable, meaning that a small perturbation would force this pendulum to either go rotate clockwise or counterclockwise. So this type of equilibrium point, which loses its stability on their small perturbation, is called an unstable equilibrium point. Unstable equilibrium point. For this case, you know that from basic physics, if I perturb the system, all right, if I perturb the system, this pendulum comes back to this equilibrium point. And again, at this equilibrium point, the moment of gravitational force is equal to 0. So in both cases, the moment of gravitational force about the center of rotation is 0. But in this case, the equilibrium point is unstable. In this case, is stable. And we're going to talk about this. For nonlinear systems, you may have more than one stable equilibrium points. We are also going to talk about other types of stable solutions, stable periodic solutions, etc. So we have talked about, again, we almost finished the very basic about how we describe the dynamic systems. We had discrete dynamic systems, one, non-autonomous continuous dynamic system, and autonomous continuous dynamic systems. F is a map, essentially, mathematically, which maps the current state and input and possibly time to our the x dot, or the time derivative of our state. And then we talk about equilibrium points. At the equilibrium point, the vector field vanishes. Because the vector field vanishes, it means that x dot goes to 0. X dot means that the velocity and acceleration, for example, in mechanical system goes to 0, and the system stays there for future time if there is no external input, and if the equilibrium point is stable on their small perturbation, systems comes back to that equilibrium point. And we said that for nonlinear system, we may have more than one equilibrium point. Thanks for paying attention.